Alright class, hello, welcome. This is the one-sided derivatives lesson that we just did in class. I'm going to just show you these words. You can pause the screen to write them down if you did not take notes. Basically though, a function is differentiable on a closed interval between a and b if it has a derivative at every inside point in that interval, and if the endpoints basically have a derivative from the right and the left-handed derivative if they both exist. So, the key here though is, for piecewise functions, if the right and left-hand derivatives are the same at a point, then there is a derivative at that point as long as it's also continuous. That is important to note because sometimes before you can even look for that, you can say, hey, this isn't even continuous, so therefore these derivatives can't equal. So we're going to show for this problem that there are right and left-hand derivatives at x equals 0, but no actual derivative. So I have a piecewise function. This is 2x and this is x squared, and it's at 0. The first thing you want to do, which makes it easier, is remember the derivative is just the slope of the curve. But for linear or for lines, the slope is always constant. So we know this is the right-handed derivative right here, and we know that the right-hand derivative, without even doing that limit formula, has to be 2 because that's equal to the slope of this line. So now we need to find the left-hand derivative at this point for this function. So the left-hand derivative is going to be the limit as h approaches 0 from the left, which means we're on that function, and we're going to use f of 0 plus h because we're at 0. So that would be 0 plus h quantity squared minus 0 squared all over h. Simplify this all out. You get limit as h approaches 0 from the left, and you get h squared over h, which is just h. Plug the 0 in, you get 0. And that's the slope of the graph from the left. Clearly, these do not equal. So the left-hand derivative does not equal the right-hand derivative. So there's no derivative at that place, at x equals 0. Okay? Graphically, what this looks like, so you could see, is this is the piecewise. Again, it's the line y equals 2x starting here. So you go up 2 and over 1, up 2 over 1, up 2 over 1. And it's the curve y equals x squared to the right or left, which looks like that. And sure enough, along this line the derivative is always 2, and along this curve as you approach 0 you can see it's flattening out and approaching a slope of 0. Therefore the two different slopes are not the same, and there is no derivative. Okay, so now we're going to review a little bit. Sketch the graph of the derivative given the value f of x. This is not that bad, but it's tricky at first when you're not used to working with these. The key is look for where the derivative is 0 first. So I'm going to graph the derivative in red. So notice at these points here, here, and here, the slopes of the tangent line are 0. So I'm going to put that this is now f prime of x, and those are equal to 0. Okay. The next thing you look for is where it changes, or it's the steepest between the two zeros. So normally that's like right here and right here. Because the slope's getting more positive, it gets positive up to this point, and then it starts getting less positive as it curves back towards 0. So at this point where it's the most positive, I'm going to put a dot up here saying the slope gets to a point that's pretty high. Same thing in between these two. It's most negative about here, so I'm going to put it down there. And then surely, as you go between these two, notice how it's getting less positive, so it's going to come down. At this point it's 0, and then it's going to start getting more positive. And again, it's getting steeper, so at this point we're going to just say it's about right here. And here we're going to put it here. So what happens is this graph ends up looking like an x cubed curve, which it should, because remember, a derivative of a polynomial is always 1 degree lower than the polynomial itself. So since this was a 4-degree polynomial, that is now a cubic. Let's do the same thing for this one. This is a 3rd-degree polynomial, so our graph should probably be quadratic or a parabola. The place where this looks like it's hitting 0 is right here. So we're going to put a dot right there. And then notice, way down here, the slope is very positive. So I'm going to put a dot way up here. And on this side, the slope is very positive, so I'm going to put that same dot right here. And as you get closer to 0, the slope gets less positive. until you hit 0, and then it starts becoming more positive. So sure enough, that slope, or that curve, represents the slope of that function as you keep going. All right, last problem. Let's review. It's basically going backwards. I tell you the slopes. I tell you a point. I want you to sketch a graph. So first thing you do with these problems is sketch the point that's given. So I have a point 0, 1. 0, 1, which is right here. Then I look at, you have to think about this as two regions. It splits at x, they connect at x equals 2. I'm going to just do this. You don't have to do this on your test or quiz. I just want to show you. That's kind of where the slopes change. So everything to the left of that line has a slope of 2. So that means going through this point, I have a slope of 2. 1, 2, 1, 1, 2, 1. So that is the slope of 2. Then the slope changes at 2 and becomes -1. And it does that forever. So this would be the graph of this scenario. This would be our function based off the slopes that were given to us, or the derivatives. Okay? Again, key for these problems, look for the starting point and then look for the slope along this line first, and then that one. And that is it.